These are your 7-1A notes on graphing exponential functions. So like I said before, this is where we're going to put the variable, the x, and in the exponent position. So the exponent is actually going to change. So we've done where the exponent was squared, those are our quadratics. We've looked at graphs when it was cubed or to the fourth, but we never looked at the graphs of what if that is the thing that keeps changing, that keeps varying. So a couple things. The parent function is of the form y is equal to b to the x power, and the b stands for base. So it's actually that changes. This is a little bit different. The parent function can change. There are different parent functions for different bases. One of the rules for exponentials is that the base has to be greater than 1. So the reason we have to have a base greater than 1 is because if you had a base of 1 and you raise it to the first power, you would get 1. And if you had 1 and you raise it to the second power, you'd get 1. And on and on and on, every number that you plugged in for x would give you 1. So that's boring. That's just a horizontal line. You can't have a negative number either. The base has to be greater than 1, can't be negative, because every other time you'd bounce back from a negative answer to a positive answer, and there would be no rhyme or reason to the graph. So here's a parent function. Anytime you graph this, your y-intercept is going to be 1, because when you plug in 0 for your exponent and you raise any number to the 0 power, the end result is 1. So remember, we're looking at 0, 1. Your y-intercept is when x is 0. So your y-intercept is going to be 1. The domain is all reals. The domain from left to right, this graph hits every single x value. Your range, though, on the other hand, are just the positive values. And the reason for that is there's a horizontal asymptote for exponential functions, and it's the x-axis. Unless, of course, you change it and you translate it and adjust, which we're going to do. This would be a parent function of growth functions, and the growth is because the base is greater than 1. So 2, 2.5, 1.5, those are all representative of growth functions. Then you have decay as well, and decay means it goes down. So if you notice, the graph is a little bit different in decay. It's now falling to the right, where growth was rising to the right. And when you have a decay model, it's when the base isn't a negative number, but it's less than 1 greater than 0. So it's a proper fraction between 0 and 1. 1/2 would be decay. 1/3 would be decay. So they're still positive, but they're less than 1 now. And what that does, we still have 0, 1 as our y-intercept. We still have the x-axis as our horizontal asymptote. Domain is still all reals. Your range is still all the positive values, because all of our graph is all above the x-axis. But now the graph is falling. So as the numbers move to the right, they get smaller and smaller and smaller. They decay. And up above, in the growth example, the numbers get larger and larger and larger as they go up in the growth. So here are the transformations one more time here with A's, H's, and K's. The H value moves it H amount of units to the right if it's positive, H amount of units to the left if it's negative. K is up if it's positive, down if it's negative. And then your A value, again, stretches or compresses the graph vertically and reflects if it's negative. So if the A value is negative, it's going to reflect it over the x-axis. It's the same for both exponential growth and decay. So nothing changes between your base if your base is something different. So your parent functions are going to look a little different. So in these first examples, I want to show you the parent function in that particular family, and then the transformation. So it asks us to sketch the following exponential functions, describe the transformation, and determine if it's growth or decay. Well, in these two examples, notice that the base is 3. Okay, so my base is equal to 3, which is greater than 1. So this is a growth. They're both growth. So this first example here, y equals 3 to the x, is the parent function for this family. And so when we graph that, we can just make a table of values like we usually do. I would like to start with 0. And so when I plug in 0, I get 3 to the 0 power, which is 1. If I plug in 1, 3 to the first power is 3. If I plug in 2, 3 squared is 9. And then we get a little too big. 3 cubed is 27. I can't really fit that on here unless I scale. I will show you a negative number. If x is equal to a negative 1, what you're going to get is 3 to the negative 1 power, which flips the 3 and makes it the reciprocal 1/3. So I won't plug in a whole lot of negative numbers in here just because it's hard to graph a third and a ninth and that sort of thing. So when I go to graph this function, 0, 1, 1, 3, 2, 9, and then I can go to negative 1 and 1/3. Now remember what we talked about in the very first page. The x-axis serves as an asymptote. As long as we didn't shift up or down any, it's still the asymptote. And so it doesn't change my actual horizontal asymptote. And so I have this growth curve, which is rising to the right, which it should, and then it kind of follows that asymptote. It should not cross that asymptote. And there is the parent function for y equals 3 to the x. To graph the second function, I know I have an h value of -2. H is equal to -2 here, which means it's going to shift to the left 2 units. I'm going to go ahead and make a table value because sometimes that's just a little bit easier to understand. And I'm going to use the same exact values. So I won't start with the negative, but I'll start with 0. If I plug 0 in to this new function, it's really going to take the 0, add 2 to it, and that's going to make it 3 squared, which is 9. So when I plug in 0, I'm getting 9. Last time when I plugged in 0, I got 1. When I plugged in 2, I got 9. So 0, 9 is going to be my y-intercept. And if you notice, where I was at 9 before, it's 2 units to the left of where I was before. If I plug in 1, 1 is really going to make my exponent into 3, and so I'm going to get 27. So I don't even want to graph that one. If I plug in 2, it's going to get even bigger. So I'm actually going to go to -1. When I plug in -1, I get 3 to the first, which is 3. So when I'm at -1, I'm at 3. And again, that's 2 units to the left of where my parent function was. And so the same thing's going to hold true for 0. It's going to take me 2 units to the left. And so the whole entire graph shifts 2 units to the left. And it still, though, goes down to that asymptote. So you could use the idea that it shifts 2 units to the left. Sometimes it's difficult to do. Horizontal is not so bad. Vertical kind of gets a little difficult, too. So if you need to, just make a table of values. You don't need a ton. And just make the values that work for you. So I really don't need to see 27. Okay, I really don't need to see anything less than the third. And then we can describe the transformation. And when I describe that transformation, I'm going to say that we translated 2 units to the left. And there's our first graph. So just a table of values. I think that's all we had to do there. On the next graph, this next graph, the base is equal to 1/2, and so we're dealing with a decay. So our graph should fall to the right. And the parent function is 1/2 x, or to the x. So the parent function is going to stick with that horizontal asymptote of the 0 x-axis. So whenever you have a decay problem, I'd actually like to flip that fraction so I have bigger numbers. So actually, I'm going to plug in 0, and 0 gives me 1, because any number raised to the 0 power is 1. I can go ahead and plug in 1. 1/2 to the first power is 1/2. But if I plug in 2, it's just going to make a really small decimal. So I'm actually going to plug in negatives. When I'm dealing with decay, I like to work with the negative numbers because they're bigger. So when I plug in a -1, that's raising 1/2 to the -1 power, which actually flips it and makes it 2. If I plug in -2, that's going to raise 1/2 to the -2 power, makes it 2 to the +2 power, and I get 4. So if I start graphing these, 0, 1, 1 gives me a half, negative 1 gives me 2, negative 2 gives me 4, and negative 3 would actually give me 8. And there you have a decay curve. It starts up high and then falls down low and hits the horizontal asymptote. So if you look at the problem in number 4, we're actually doing a few things to it. The 3 on the outside is the A value. It's going to change the slope of this curve. And then the -1 is going to drop everything vertically down 1. So when it gets really complicated like that, we just go ahead and make a new table of values. So I still want to flip that half. I'll do 0. But when I plug in 0, I'm not going to get 1. I'll get 1 for the 1/2 to the 0 power. But then I got to multiply that by 3 and subtract 1. And so I end up with 2, 0, 2. So last time I had 0, 1. Now I have 0, 2. If I did that right. And so I know it looks like I should have shifted down 1, but because I'm multiplying by 3 and shifting down by 1, it doesn't have that result. So using that whole translation idea doesn't really help you here because we have multiple things going on. When I plug in 1, 1/2 to the 1 power is going to give me a half, times 3 is going to give me 3 halves, take away 1 is going to leave me with a half. So 1 gives me a half, just like the other one gave me a half. It's really weird that that would happen, but because of the 3 times it in the way that that all works. 3 1/2 take away 1 is going to leave you with the 1/2. When I plug in -1, it's going to flip the half to make it 2. I'm going to times the 2 by 3 and get 6. Subtract 1, I end up with 5. So -1 gives me 5. And we'll do one more. If I plug in -2, that will flip my half and make it 4. 4 times 3 is 12. -1 is 11. So -2 gives me 11. And there's my other sketch. Okay, so I'm not going to worry too much about where that ends up. I believe the actual, if we come back here, oh, sorry, wrong way. We're just doing sketches here, and so we could say in this one that it was stretched vertically, and that we were translated down 1 unit. In this last one, it will flip, and so I'm actually just going to show the number 6 right here rather than doing 2 graphs for time's sake. I'm going to go ahead and plug in values that make this work. So I'm going to plug in a 1 value. When I plug in 1, I get 0 because 1 minus 1 is 0. 2 to the 0 power is 1. 1 times -2 is -2 plus 3 is 1. So 1, 1 is going to work here. And I'm not doing the parent function. If I plug in 2, when I plug in 2, 2 minus 1 is 1. 2 to the first is 2 times -2 is -4 plus 3 is -1. So 2 gives me -1. And when I plug in 3, it's really going to look like 2 squared, which is 4 times -2 is -8 plus 5 is, or plus 3 is -5. So 3, -5. Now you can see this is actually a growth. It's still going to be growth, but because of this -2, we're actually going to reflect over the x-axis. So usually the growth would be going up and to the right. Now we're going to be going down and to the right. The other thing I want to mention is that +3 is actually our new horizontal asymptote. And so I'm going to approach that, and then I'm growing in a negative sense. I know it's weird, but I'm growing to the right just in a negative sense. And the other graph would have been going up and to the right. So it's a reflection over the x-axis. So in the lesson summary, I just want you to determine if this would be growth or decay. And in this particular problem, a little bit different, I want you to describe the transformation. So there is no number out in front that's being multiplied, or you can consider that like a 1 for your A value. So it's not stretched, it's not compressed. So just describe what that -3 and that +1 does. You don't have to worry about graphing them. We'll work with this one on the graphing calculators. Good luck.